Today we're going to solve logarithmic equations. So far this unit we have manipulated logarithmic expressions and we've graphed logarithmic functions. So now we're in the equations section of the unit where we're going to solve for x. In other words, we're going to try to figure out what the value of variables are. So I've added the properties of logs to the top of your notes page. Remember from last lesson that when we're multiplying powers, the exponents get added. Here, when we're dividing powers, the exponents get subtracted. Here, if we're raising a power to an exponent, then we multiply exponents. So keep those in mind because we'll still be using those. And then there's some other log properties at the bottom. This is one that we're going to use a lot. Notice what's happening. If we want to isolate an argument, which remember the argument is this part of the logarithm. So what we can do is we can make a base that has the same base as the logarithm, and then essentially we can isolate those arguments. And remember, in the process of solving equations, we generally want to isolate things. So keep that one in mind. It's going to be pretty helpful. Now let's go to these side notes here. So when we're solving logarithmic equations, we want to do everything we can to manipulate each side so that it has just one logarithm on each side. And then if the original equation has a log, then make sure you check your final answer, your final solution, so that you know that all of the arguments are positive and eliminate any negative arguments. So let's talk about why that is. If I go back to a logarithmic function, remember with logarithms, the domain restriction on logarithms is this vertical asymptote. So the x value right here cannot be 0 or negative. So we've got to make sure that none of our solutions include the number 0 or a negative number. So let's go back here. And the first thing I'm going to do is kind of look at the different kinds of equations that we see on this page. I want you to notice for examples 1 and 2, you have logarithms on both sides of the equal sign. They do have the same bases, so that's important. Now for example 3 and 4, they're close to example 1 and 2, except for now we don't have logarithms on both sides of the equation. Notice there and here. So that means that we have kind of a different process for solving for x. And then finally, example 5 isn't even a logarithm, it's an exponential equation, so we'll have a different process altogether. All right, so let's go ahead and dive into example 1. I want you to notice it's asking us to solve for x. Now, the first thing I want to do is condense everything as much as I possibly can. So I'm going to go ahead and rewrite that as log base 7 of x squared instead of 2 times that log part. And then we have log base 7 of 9. Now, if you look at this, it's kind of, I think, intuitive to see what to do next. Notice if we have log base 7 of something is the same thing as log base 7 of something else, then hopefully it makes sense to you that the somethings are going to equal each other. Now, if we look at the property above, we can kind of apply that property and show procedurally what we're doing. So if we make a base of 7 on both sides, look at how this relates to that. If we have a base of 7 here on the left side, then this simplifies down to just x squared. And if we have 7 to log base 7 on the right side, then this simplifies down into just a 9. And now we have an equation we've seen all year long where we can square root both sides and find that x is equal to either positive or negative 3. But wait, we're not finished because remember, there's a domain restriction on logarithms. X cannot be anything negative. And here we get a negative solution, so that needs to be eliminated to leave just x is equal to 3. All right, next equation here. First thing, we want to condense everything as much as we can, and we can because remember the whole logarithm is an exponent, and right here exponents are being added, so we can rewrite this so that powers are being multiplied. And then now notice we have log base A on both sides. We can essentially make a base A for both sides of the equation, and then that's going to isolate our arguments only. So we'll have x times x plus 4 is equal to 12, and now we simplify and solve. So we've got x squared plus 4x is equal to 12. We're dealing with quadratics here, so we move everything to one side and get x squared plus 4x minus 12 is equal to 0. Here we factor. This has to be an x and an x. We need what multiplies to negative 12 and adds to 4. So negative 6 and positive 2 would be our solution. So x is either equal to 6 or negative 2. But again, wait, x cannot, or the arguments here in the original equation cannot be negative. So even though this argument would be positive if we plugged in a negative 2, this one would not. So we have to eliminate that from our list of solutions. All right, so next, we can't use the same procedure for solving in example 3 and 4 as we did in example 1 and 2. So let's see what we can do. The first thing we can do is go ahead and condense that left side, and we end up with log base 4 of x times x minus 3. Why is that? Because exponents are being added, so powers get multiplied. And then we have log base 4 of x squared minus 3x is equal to 1. And notice what we can do here. We can just use kind of that snail method, or we can recognize that this is the base, this is the exponent, and this is the argument or the power. So we can go ahead and rewrite this as 4 to the first is equal to x squared minus 3x. So let's do that. 4 to the first is equal to x squared minus 3x. 4 to the first is just 4. And now we're again in quadratics land, so we can subtract 4 from both sides and get x squared minus 3x minus 4 is equal to 0. So now we're factoring. We're finding what multiplies to negative 4 and adds to negative 3. So x minus 4 and x plus 1 is equal to 0. So x is either going to be a positive 4 or a negative 1, but we have to check those, and notice we cannot have a negative 1 in for that first logarithm or the second one. So it has to be 4 only. All right, next question, and if you feel pretty confident on this, try to do this one on your own. All right, remember, if no base is shown, it's automatically a base 10. So first thing, recognize that this whole thing is an exponent, so we have exponents being subtracted. So if we wanted to condense this, we would want to divide the powers. So it's x plus 5 over x plus 3 is equal to 1. Now remember, this is our base, this is our exponent, and this is our argument, which is the answer to the power. So we can say 10 to the first is equal to that. 10 to the first is just 10. And then notice, if we want to get rid of the x plus 3 in the denominator, we would multiply both sides by x plus 3 to cancel. And then we can distribute that 10. So we get 10x plus 30 is equal to x plus 5. So I'm going to subtract x from both sides. And I'll have 9x plus 30 is equal to 5. Then subtract 30 from both sides and find that 9x is equal to a negative 25. Divide both sides by 9 and get x is equal to a negative 25 ninths. Now initially my instinct is to say that this is not an okay solution because it's negative, but let's go check it in the equation. So negative 25 over 9 is about negative 2.7. So if we plug in a negative 2.7 here, it's still this argument is still positive. And if we plug in a negative 2.7 here, this argument is still positive. So our solution can be x is equal to negative 25 over 9. All right, next one. Totally different equation. We are looking for the value of x still, but we've got no logarithm, we've only got an exponential. So let's simplify or isolate e as much as we can. So I'm going to divide both sides by 25. At this point, we have e to the x is equal to 4, which is kind of nice. And remember, here we need to get that exponent weighed down or pulled out of that superscript. So remember, we want to do a log base e, but remember what that is a natural log. So I'm going to do the natural log of both sides. And remember, if you have a natural log of e, this cancels out and we end up with x is just equal to the natural log of 4, and then you can just put that in your calculator. All right, so we're going to move on to some word problems now. And the first word problem is really closely linked to the project you guys are doing right now, so let's read it together. The first note on a piano keyboard corresponds to a pitch with a frequency of 27.5 cycles per second. With every successive note you go up the white and black keys of a piano, the pitch multiplies by a factor of the 12th root of 2. So the formula for the frequency of the pitch sounded when the nth note of the keyboard is played is given by this function right here, super messy looking function. So if one pitch on the keyboard has a frequency of 1760 cycles per second, how many notes up the keyboard will this be? So if you counted from the very left, if that's note 1, and then we kept counting up, we want to figure out which note on the keyboard has a frequency of 1760. So let's do this. So we know that the frequency is 1760. So I'm going to go ahead and plug that in here. So I'm going to change my equation so that it's 1760 is equal to 27.5 times the 12th root of 2 to the n minus 1 power. Keep in mind, we have a variable and an exponent. And the only way we can isolate a variable and an exponent is to use logarithm. So we're going to eventually use a logarithm here, but not quite yet, because we need to get this part right here isolated first. So we're going to use our Algebra 1 concepts to get that 2 to the n minus 1 power isolated. So the first thing we want to do is divide both sides by 27.5. Now, if I divided that out, I'd get this long, messy decimal, and I don't want to deal with that. So I'm just going to leave this left side as 1760 over 27.5. And now on the left side, I just have the 12th root of 2 to the n minus 1. Now we got to get rid of that 12th root. Hopefully you're thinking, well, if you want to get rid of the 12th root, we want to take both sides to the 12th. So now we've isolated the 2n minus 1, or 2 to the n minus 1, and on the left we have 1760 over 27.5 to the 12th, and now we can introduce logarithms. So notice our base here is a 2, so that's what we want to use for our log base. So we're going to do log base 2 of 1760 over 27.5 to the 12th is equal to whatever we do to one side, we do to the other. Log base 2 of 2 to the n minus 1. Now remember what happens here. That part pulls the n minus 1 out of the exponent. So now we can simplify this down even further into log base 2 of 1760 over 27.5 to the 12th is equal to now just n minus 1. At this point, we want to go ahead and isolate our n value, so we're going to add 1 to both sides. And we'll have n is equal to log base 2 of 1760 over 27.5 to the 12th plus 1. And then the last thing you want to do before you pop it in your calculator, so we need to deal with that. Remember, if we're taking a power and raising it to an exponent, then we multiply. So we want to go ahead and have our final answer as 12 times log base 2 of 1760 over 27.5 plus 1. And then from here, we're going to use our calculator. Remember, we don't have a log that has a button immediately on the calculator. This is a log base 10 and this is a log base E. So we want to push math and then arrow up until we get to letter choice A, where we can enter our own base. So I want to do log base 2 of 1760 divided by 27.5. And then I forgot to put in my 12, so I'm going to put times 12 here, and then plus 1. And if I do that and push enter, I find that this frequency corresponds to the 73rd note on the piano. All right, and the last question. A population of a certain country in 1999 was 287 million people. In addition, the population of the country was growing at a rate of 1.3% per year. Assuming that this growth rate continues, the model P of t equals 287 times 1.013 to the t minus 1999 represents the population P in millions of people in year t. According to this model, when will the population of the country reach 482 million people? So notice here, you guys have seen this before. This is an exponential growth problem. So notice this is 100% of the population is the 1, and then we're adding 1.3% right there. So, and then notice this is your starting amount in millions. And then this is, because we're talking about years rather than number of years past, then we have to find the difference between the current year and 1999. So you've seen this before. It's probably been a couple years, but you have seen this formula before. Now, our job is to figure out what the time equals, and you've got to use logarithms if we have a variable in an exponent. So let's go ahead and do what we did before. We know that the population needs to be 482 million, so let's put that in place of P of t. So we're going to have 482 instead of P of t equals 287 and then 1.013 and then t minus 1999. Okay, so we eventually need to get t out of the exponent. Remember, we want to isolate this as much as possible before we start taking logarithms. So the first thing we're going to do is divide both sides by 287. And again, I'll get a really messy decimal there, so I'm just going to leave it as 482 over 287. And at this point, we can take a logarithm. Now notice, what does our base need to be? Well, if you recognize what you're looking at right here, your base is this. And the cool thing is that now with new technology, you can enter any base that you want. So we're going to use that messy base. What we need to do is we're going to take log base 1.013 of 482 over 287. Remember, whatever we do to one side, we have to do the other. So on the right, we have also log base 1.013 of 1.013 to the t minus 1999. And notice, remember, this thing pulls that exponent out of the superscript, and we end up with log base 1.013 of 482 over 287 is equal to t minus 1999. And then finally, all we need to do is add 1999 to both sides. So our final equation that we can use to figure out what t equals is log base 1.013 of 482 over 287 plus 1999 is going to give us the current year. And now we move back into our calculator. Remember, we want to do a log with a custom base, so let's go to Math and then arrow up. We want a log base 1.013 of 482 over 287, then plus 1999, and we find that it's going to be about the year 2039. Those are really great applications for logarithms.